All right, so on this reaction, the oxidation. So oxidation with osmium tetroxide, so OSO4, is an oxidation of that double bond. Right? So oxidation typically means we're going to make more carbon-oxygen bonds. All right, so we're going to look at this double bond, and we're going to add two alcohols across that double bond. So in the reactions before, we just added one. Now we're actually going to add two. So it's going to take an alkene to a glycol, and it just means a diol. So there's going to be two alcohols right next to each other. Syn addition means they're going to add to the same side, right? So we're going to add them to the exact same side. So let's see what that looks like. Let's draw our cyclopentene. And then where the double bond was, syn means they're going to be on the same side. So I went wedge, but you could have done dash. We're going to put an oxygen. We'll put our osmium is still there. And then we have the other two oxygens, right? We had our 4 oxygens. And what you see on this first step is the osmium is just delivering those oxygens, right? It's just pasting those oxygens right onto that double bond, right? They add to the same face because they make a ring. And so they're going to always be both wedged or both dashed. The second group is just to cleave off the osmium, right? So just like on the previous ones when we had the mercury or the BH3, we don't actually want that in our product. We actually want our alcohols. So this next group is just to cleave, right? This is just to get rid of that osmium group. So what we see as our product is we still have the cyclopentene, and then our alcohols on the same face. And they add syn, so I drew these wedged, but you could have drawn it as a dashed version as well. Okay. As long as you show that they're syn. So it doesn't control if it's wedged or dashed, it just tells you they both have to be the same thing. And so this makes my diol, right? So they're going to add to the same face. Let's try one. So it'd be step 1 would be OSO4. Step 2, NaHSO3 water. All right, so show me what you would get in that reaction. All right, so go ahead and pause the video and give that a try. All right, so let's see how everyone did. So same as before, our attention should go right to the double bond. And we know each carbon that's part of the double bond is going to get an alcohol. So the first thing I would do is let's just draw our molecule exactly the way it is. All right. And then those two carbons that were where the double bond was, each one's going to get an alcohol. And they have to be syn. So I can either pick both wedged or both dashed. All right, so not too bad. So you're always just going to kind of focus in on that double bond. When you see the osmium reagent, you know you're going to get this syn diol. Syn meaning that they're adding to the same side, diol meaning two alcohols, right? And they go right on those two carbons of double bond. No rearrangement, so it's literally always going to go on those two carbons. So that kind of makes it a little bit easier. This next one, ozonolysis. So we're actually going to use ozone, so O3, to cut a double bond. So this is going to be one of the first reactions where we actually cut a double bond. All right, so what this is going to do is give you two carbonyls in place of the double bond. All right, so if you kind of bear with me in this silly analogy, but like if you think my fingers are that double bond, you're actually going to cut the double bond and split it into two. And then the fingertips where that double bond used to be for each side become carbonyl. So you just put an oxygen at the end. So if we're looking at this molecule, we're going to cut this bond. And at the end, we're going to put a carbonyl. So let's draw it. So this molecule, and let me highlight the pieces. So if I put this one in orange, it's going to be one group. And so I'll draw that first. So we keep our carbon. our CH3 goes on top. We have a CH3 this way. And now this is where my double bond was. And so instead of having to be a carbon-carbon double bond, we get our oxygen. So there's our carbonyl. And then plus the other half, and so let me put that in like a green so that you can see the difference. All right, is now we get our double bond O. We have our H, CH2, CH3. And then at the end of that double bond is an oxygen. And so here are my two carbonyls, right? A carbonyl is a carbon-oxygen double bond, carbon-oxygen double bond. Right? And so we're literally just cutting that carbonyl or that alkene or the double bond and putting a carbonyl in its place. Okay? Now, this was a reducing agent. Okay? And so that just leaves it the way it is. Now, if you did the same reaction, so let's take this same one. And we're still going to do step one is O3. But on step two, we put some oxidizing agent like peroxide. What it's going to do is anywhere it was an aldehyde, see how this hydrogen tells me that it's an aldehyde? That's going to get turned into a carboxylic acid. Right? So ketones, right? This carbon has a carbon on either side of it. We're going to leave it alone. But anywhere you have the aldehyde, instead of having an aldehyde, you'll have a carboxylic acid. All right, so let's see what it looks like. So the first molecule will stay exactly the same. Now it's the second one that changes. We have a carbon, and then instead of having that hydrogen there, right, because hydrogen will be coming off of it, we actually get an OH. And then the rest of the molecule stays the same. All right, so the difference is if we have our reducing agent on the bottom, it just stays exactly how it is. We just cut that double bond. If we have an oxidizing agent, if it's an aldehyde, right, there's a hydrogen coming off that carbon, it gets converted to an OH, which gives us in total a carboxylic acid. All right, so that's kind of the difference. And so let me just highlight those groups. So if we have here's a carboxylic acid, if we have an oxidizing agent, and here's my carboxylic acid. So this is one of the few reactions where we actually cut the carbon molecule in half. All right, we don't do it very often, so this one's kind of unique that we're actually cutting the molecule. All right, so this is a one reaction you've probably heard of before. So if you hear about like hydrogenated oils or hydrogenated fats, this is actually the reaction they're doing. So hydrogenation is just reducing double bonds. And so if we look at the reaction here, we have an alkene, right? So our double bond, we're going to add hydrogen across it and get cyclohexane, right? So we're just erasing that double bond. We're taking something that's unsaturated and making it saturated. And that's where that term comes from, because you're saturating the molecule with hydrogens. It's literally the most amount of hydrogens that molecule can have. So it's saturated with hydrogens. All right, so the way this works is you're going to take an alkene, react it with hydrogen, but you need some transition metal catalyst, right? So you're going to need a catalyst. And I want to highlight that. And actually, let me put that in a different color so that we can kind of pay attention to it a little bit. It's going to be a catalyst. And so if you remember, catalysts help speed up reactions, but they don't show up in your product. All right. And so the reason I want to spend a little time on that is if it's a catalyst, it's not going to show up in your product. All right. So the biggest mistake I see people make is they want to add palladium, they want to add platinum, they want to add nickel. So any of these reagents down here, they want to add it to the molecule, but it's a catalyst, so we don't see it. Right? The other thing that we're going to see is sometimes it needs a little help, so we can put some temperature. So if we need, sometimes we have to heat it up. We add some pressure, right? 3 atms is just the amount of pressure. So sometimes we just got to kind of cook it, right? And so we just put hydrogen in there. A lot of times you actually put in the sealed vessel where you're pumping hydrogen in. So you're just putting a ton of hydrogen to force the reaction to go forward. A couple other things about this is they're going to add syn. So that means they're going to add to the same side. Right? So if you showed the hydrogens, they would add to the exact same spot. All right, so let's see what this would look like. So let's take a molecule. So if we take our double bond, The reaction would just be H2 and some catalyst. You could write the temperature, the pressure. So sometimes you'll see it. Sometimes you'll just see it generically as hydrogen over some metal catalyst. So go ahead, pause the video, give it a try, and then we'll do it together. All right, so how did everyone do? So if we draw the molecule, you can actually draw this one of two ways. You can do like I've done above and just literally erase the double bond. Sometimes people really like to see where the molecules went. So let me just kind of color code everything. If I have my two hydrogens, they would have added across that double bond. You can do dashed or wedged, either one. They're just going to add syn to each other. So they're going to point in the same direction. All right, so really easy. We're just adding hydrogens across the double bond. And a lot of times people will draw it just like we did above, where you're just erasing the double bonds. Because remember, the hydrogens are always implied. Last trick to this, just make sure to add syn. So those two hydrogens will always add the same direction, either both wedged or both dashed. And here's exactly why. All right, so the way this works is you're going to take your metal and you're literally going to coat it with hydrogens. And then it's just going to stamp on the double bonds. So you're just going to coat that metal with hydrogens. And then it's just going to stamp across the double bonds. And since we're stamping them at the same time, they're going to point in the same direction. All right, so kind of a neat way the reaction adds those hydrogens across the double bond. One last set, and this is a little tricky because it's similar to what we've done before, but then kind of mixes it up. So you can add HBr across an alkene. Right? And so if you do what we just did before at the very beginning when we start talking about alkenes, is you could take a double bond and you add HBr. It follows Markovnikov's rule, right? So it's going to have Markovnikov addition, which means we'll take our molecule and we add the bromine to that more substituted carbon. Okay? And the hydrogen that was here would have come off that least substitute. Right, the other one we can do is now if we add peroxides, and a lot of peroxides would be things like H2O. So a peroxide is just anything that has an oxygen-oxygen bond. And hydrogen peroxide is actually kind of the peroxide you would buy at the store. It has a lot more water, but that hydrogen peroxide. It actually, so when you have your HBr and a peroxide, you're going to do anti-Markovnikov. So the bromine is just going to add to the other spot. So we'll draw our molecule, and now the bromine will come off the end. And so it's kind of a neat reaction where by doing it in the presence of a peroxide, we can switch where it adds. Right? So if it's just HBr, HCl, it's going to follow Markovnikov's rule and add to this more substituted carbon of the double bond. Right? We still lose the double bond, and the bromine comes off that more substituted carbon. If we add a peroxide, we add to that least substituted. And just the reason it works is if it's just HCl, HI, HBr, it's going to give the Markovnikov products, right? So essentially that more substituted carbon. If you do this in the presence of peroxides, right, all of a sudden, instead of doing that addition reaction, we're doing our radical mechanism. Right? And so we just talked about on the previous slide, our peroxide is when we have two oxygens together. So when we react that peroxide, it's going to split that oxygen-oxygen bond, and you get these two radicals. Okay. Now, these two radicals react with the HBr and give us a bromine with a radical. And the reason that's important is now, instead of the hydrogen adding first, like as we saw with HBr and a double bond without any radical, the bromine will react with the double bond and will make this bond. We get a radical on the more substituted. So the more substituted that radical is, the more stable it is. So that's why it goes to the more substituted carbon. And now it can just perpetuate that reaction, right? Because it can use this to steal one of the hydrogens, and this makes our product. Okay? And this just kind of highlights why in the presence of peroxide, we're going to add anti-Markovnikov, right? So still the same rule if there's no peroxide, that bromine, the chlorine is going to add to that more substituted. If we add peroxides, we do anti-Markovnikov. So that halogen is going to add to that least substituted carbon of the double. All right, so I know we've done a lot of reactions, so why don't you go ahead and pause the video, try this review, and then we'll do it together. All right, let's see how everyone did. So let's just start here on the far right. So if you have Br2, I think that one's actually one of the easier ones, because what we're going to do is look at our molecule and know that we're going to add a bromine to each carbon that's part of the double bond. So we'll add one bromine on the end, one bromine in the middle. So if we look at the two, this is where my double bond was. And now each one just gets a bromine. So we'll put a bromine on one carbon, a bromine on the other. Okay. So we just focus on the double bond, and we add a bromine to each carbon that was part of the double bond. Same thing with Cl2 and water. Now the difference is when you have water mixed in with it, you're going to add the water molecule to the more substituted carbon and the halogen to the least. All right, still no rearrangement, but we're going to add it to that more substituted. All right, in terms of the water goes to the more substituted carbon, halogen to the least. So let's draw our molecule. We get a chlorine pointing one direction, our alcohol pointing the other. And then in this case, we get plus HCl. And that's just to account for the chlorine that we didn't use and the extra hydrogen that water lost when it shows up as an alcohol. Okay. Last one, or sorry, not last one, the next one, we have a few more. You're going to add BH3 followed by peroxide and sodium hydroxide. Remember, anytime you see BH3, you're going to add to the least substituted carbon. And so we would add these sequentially. So we're going to add an alcohol to this least substituted carbon. So let's draw our molecule. All right, and then off the end, we get our OH. All right, so anytime we see BH3, we're going to add anti-Markovnikov. So we're going to add that alcohol to that least substituted. Osmium, so OSO4, we're going to add a diol. So we're going to add two alcohols. And so we add our two OHs to the same side. All right, so we see that OSO4, we're going to add our two alcohols. I kind of cheated. I should have written the sodium sulfate. All right, so but when we see osmium, we should always think that we're going to add those alcohols. The next one, ozone. All right, we're going to cut that double bond. All right, so we'll cut the double bond. We're going to split it into two molecules. All right, so we'll have our two molecules there. And then at the end, right, it goes 1, 2, 3, 1, 2, 3. And so then at that double bond, we get an oxygen. And then on the other side, we just have this lone carbon. So it'd be a CH2. Now, this is the one where it depends. And I didn't put the second step, right? But this would be step 1. And then step 2 would tell us whether what we're going to do to this, right? So if it's just with our sulfur, then we just leave it the way it is, where these are hydrogens. Right, so this would be an aldehyde because there'd be a hydrogen implied, and there are two hydrogens. If in the other case, if instead we use peroxide, right, so if we did that as step 2 instead of this one, maybe the arrow is the wrong thing, and so instead, let's put or, then we would draw the same molecules, except they become carboxylic acids. Right. And so that's kind of the difference, right? So if we see the reducing agent on the bottom, then we get it as the aldehyde. Remember, if it's a ketone, we just leave it alone. But if it has that hydrogen, we make them into alcohols. Right. Last one. Now, this one can rearrange. Typically, if it's several carbons away, we'll leave it alone. So on this one, I actually don't think it'd rearrange. If it's next door, then yes. So I think if it starts to be a couple of carbons away, it's just going to stay where it is. And so this one just gives you an alcohol, the more substituted. All right, so hopefully this kind of gave you a nice summary of all the different reactions. All right, so let's try this. So here are a couple more. So go ahead, pause the video, give it a try, and then we'll do it together. All right, let's see how everyone did. So again, if you see the bromines, where it's Br2, we're going to add one to each carbon that's part of the double bond. So let's just draw our molecule the way it is. So we get our cyclo group, so cyclohexane. Our two carbons on the other side stay there. And then now we're going to add our bromines, but remember they add trans. So you're going to make one of them wedged, the other one dash. If you'd done the opposite and made the top one dash and the bottom one wedge, perfect, right? Exactly the same. Anytime we see osmium, remember that's going to tell us that we're going to make a diol and a syndiol, right? Meaning they're going to add to the same side. So osmium is going to yell out syndiol. So we're going to draw our cyclopentane. We keep those two carbon groups coming off of it. Okay. And then where our double bond was, we get our two alcohols. So remember, it doesn't matter if they're both wedged or both dashed, they just have to be the same. Okay. So if you drew the dashed instead, that's fine. Right? They just have to be syn, right? They're going to show the same direction. On the next one, we have H2SO4 and water, right? So we're going to mix the two together. We would expect that the alcohol is going to follow Markovnikov's rule, so the alcohol should be on the inside. But we can actually do a methyl shift. So this methyl group is actually going to move over one. So we're actually going to move that methyl group over. And so let me show you what that looks like. So this is that methyl group that moved over, right? So it shifted, and what it did is rearrange that carbocation intermediate so that my alcohol can add there. The next one is BH3 on the exact same molecule. But remember, BH3 adds anti-Markovnikov, so it's going to add to that least substituted carbon. So when we're looking at this, we're going to add it to that least substituted carbon of the double bond with no rearrangement. So we'll draw the molecule just the way it is. And I'm going to highlight where the double bond was. And so we just get the alcohol off the end. Last one on here is mercury acetate. Right? And so we typically, and I left off the water. So we have mercury acetate and water. And when you see mercury, it should yell out at you putting an alcohol. Right? We're going to add an OH, right? That's what should kind of yell out at you when you see mercury, is that we're going to add an OH, and you're going to add it to the more substituted with no rearrangement. So in some regards, I actually think from drawing the product standpoint, it's easier because you don't have to worry about some rearrangement. You're just adding an alcohol to the more substituted carbon of the double bond. So if we look at our molecule, we can redraw it exactly the way it was. And then wherever the double bond was, we pick the more substituted, and that gets my alcohol. All right. So acid and water follows Markovnikov's rule, so the alcohol is going to add to the more substituted, but with the possibility of rearrangement. We can do the hydride shift, so it's a hydrogen with its electrons, or we can do a methyl shift, which we saw here, right? Because there's no hydrogens implied, so we move the methyl group. BH3 adds anti-Markovnikov, so it's going to add to that least substituted, no rearrangement. Mercury adds to the more substituted, but no rearrangement. All right, last set, let's try just the last couple. All right, so give this a try. So pause the video, draw these products, and then we'll do them together. All right, so let's see how everyone did. So when you see hydrogen and palladium, you're just going to add hydrogen across that double. All right, so if we draw this molecule, we're going to draw the carbon framework exactly the same way as it was. And if you want, you can actually be done, right? So all those hydrogens are implied. If you want to show the hydrogens, you can, but you don't have to. So if you wanted to show that you added those hydrogens in, then you can, but you don't have to draw them out, right? So in the zigzag form, the hydrogens are implied. And the next one, we're adding HBr. It's going to add Markovnikov's rule. So it's just like we did with the water reaction. But it has the possibility of rearrangement. So we would get a secondary carbocation as our intermediate, and then our methyl group would shift over. So what I want to highlight is this methyl group is going to rearrange, just like we saw for the alcohol group on the previous page. So then what we get is that methyl group moves over where the double bond was. And now my bromine adds there. Right? And it's because we made a secondary carbocation. So then we got a methyl shift and it moved the carbocation to a tertiary. And then my bromine can add. All right, so we get that methyl shift. If you see Br2 or Cl2, we won't rearrange, right? Just like we did on the top. So before we would have added right across the double bonds. But when it's in the presence of water, the halogen will go to the least substituted carbon of the double bond. The alcohol is going to go to the more substituted. So we're still just adding to these two carbons, no rearrangement. And what you'll see is the alcohol will add to the more substituted, the bromine adds to the least. Okay? And then we get plus HBr to account for the bromine and the hydrogen we lost. They add anti, meaning one's pointing up and one's pointing down. Last one. So anytime you see ozone, we're going to cut this molecule. Right? And so we're going to put carbonyls in its place. So let's redraw the carbon framework just the way it was. So let's start with the left. So we get that group. And then here was my double bond. And remember, we're just going to turn that into a carbonyl. All right, we can do the same thing on the other side. There's a carbon here, so it's a CH. And so we'll draw that group. So we get our CH with a double bond. All right. And then the last part of this is it's a reducing agent on the bottom, so we can just leave the groups as they are. If it had been peroxide, we'd actually convert these to carboxylic acids. So if they're an aldehyde and there's a peroxide on the bottom, they turn to carboxylic acids. If it's a reducing agent, so the dimethyl sulfide, we just leave them as is.